Everybody, thank you very much for joining us. Today's webinar, as Susan mentioned, on boiler water treatment, it's a topic which has been asked for by many of the audience members in the past, but not only because of its overall importance in properly operating and maintaining a boiler system, but the mystery that seems to exist out there relative to its perceived complexity. Now, to face it, if you're like me, chemistry is a complex subject, and the variables that exist in the water that we introduce into our boilers and the associated piping and components is involved, not only posing problems in its control, but also the associated damage to the boiler and the system if the proper chemistry is not followed and then maintained. So as Susan mentioned, today assisting me is Debbie Bloom, who is the principal consultant for NALCO, and who has an extensive background, I must say, in the treatment of feed water and boiler water. In other words, the treatment of water before it goes into the boiler, and then the proper treatment while the water remains in the vessel before leaving and doing its work in the system. So it's our job today, Debbie's and mine, to take some of the complexity out of the water treatment subject. And then we would like to present it to you in as easy to understand terms, but still while not diminishing the essential elements which go into it. Therefore, from a macro perspective, what we are going to be covering today includes 6 topics. Number one, we want to briefly review why water treatment is so important, just to kind of get us all properly focused. And then next we'll look at what needs to be removed from the water in order to maximize the efficiency and reliability of the boiler system. We'll also look at what these boiler systems can withstand in terms of dissolved minerals and gases without being compromised. And this will vary based on the operating pressure of the boiler and the temperature. Then we'll discuss what we've found to be the best long-term approach to water treatment. And then we will conclude and talk about this approach as it relates to both the mechanical as well as the chemical aspects. Beginning with why water treatment is so necessary, we need to start with really an appreciation of the substance. Water is an excellent transporter of heat. Regardless if it's transporting heat in a hydronic heating system as a liquid, or if it's gone through a change of state and it's in a vapor for a process. You take a look at water, it's relatively cheap. Of course, it's bountiful in its supply, and it's just a great substance. However, as you will be seeing, water contains minerals and gases which, when heated, will lose their solubility, and they'll become very hazardous to the boiler and its connected components. And this then results in a waste of valuable energy while just shortening the life of the asset. I also wanted to mention before we go any further today that we will be including both steam, 0 to 300 pounds operating. 0 to 300 pounds is the range we'll be covering. And then we'll also be covering hot water systems, which Debbie will be handling. And though we intend to provide you with the essentials in easy to understand terms, we don't want to get into the weeds too deeply during a 45 or 50-minute presentation. It's just not possible. But what we've prepared is certainly more than just a basic tutorial of the do's and don'ts. And as such, we really hope that you walk away with several. Now, I mentioned why we treat boiler water to avoid the negative consequences, but to elaborate a little further, what we are trying to avoid, and as you can see on the screen, is the formation of scale and sludge accumulating on the heat transfer surfaces as the minerals fall out of solution when they exceed their solubility at higher temperatures. Now, at the same time, we also drive off corrosive gases such as oxygen and carbon dioxide, which can result in corrosion. Now, all of this activity results in efficiency loss and or the shortening of the asset's life as corrosion eats away the carbon steel. But that's not all. Improper water treatment also affects the quality of the steam going out into the system as well as its purity. So let's just say we have a sterilizer requiring dry steam. Certain elements in the boiler water can cause an unstable water level or foaming to occur at or near the steam nozzle, allowing the steam to exit while carrying water droplets within it, thereby reducing the steam heating capability within the sterilizer itself. And then there's the issue of steam purity. And here we're concerned with the amount of non-water components contained within that steam. Now that's usually measured as sodium ion and silica, which if present can certainly cause havoc within the many systems that we encounter. You know, when you look at a glass of water, it seems pure and benign, right? But there are many elements covertly residing in this substance and only reveal themselves when heated, causing them to lose their solubility, as I mentioned, and then fall out, so to speak. For instance, we have the minerals of calcium and magnesium, which I like to refer to as the hard-scale formers, which can insulate the heat transfer surfaces, as you see in the picture, causing not only tremendous fuel waste, but overheating of the metal as well, meaning downtime and, of course, costly repairs. And then there's the TDS components, the totally dissolved solids. Calcium and magnesium are part of this group, but it also includes sodium, silica, chloride, sulfates, and alkalinity carbonates. These two are dissolved minerals which you can't see, which can cause major system upsets and excessive surface blowdowns, resulting in water, energy, and chemical waste, if not properly controlled. And finally, we have the dissolved gases present in the water in the form of oxygen and carbon dioxide. Now, these are really killers to a boiler system, all the way from the feed water through the condensate return system if they're not removed. Now, looking closely at the waterside corrosion picture, you can see pits which have formed on the waterside surfaces of this fire tube boiler, and this led to a complete retube. Obviously, very costly, to say nothing about the loss of revenue due to downtime. The question now is, okay, we have various elements in the water which need to be addressed. What specifically are they, and to what extent may they remain in the boiler system? Now, for this answer, we will be referring to the ASME guidelines, which are broken down according to a number of categories, including feed water, boiler water, fire tube and water tube boilers, and then finally the operating pressure and its temperature. Then, under these various breakdowns, you find the elements seen on the screen which need to be controlled based on the aforementioned conditions. And Debbie will be reviewing these in detail in a few minutes. So in the final analysis, what we as an industry have determined as the best, most effective, and efficient way to control these destructive elements within the boiler system is through employing both mechanical and chemical solutions. Because if we employ only one of these, problems will surely occur involving energy losses, excessive costs of operation, including downtime, and unexpected capital outlays. So we need a combined solution. For instance, what if we were to employ only chemicals? Let's say that would include phosphates or polymers to control the calcium and magnesium and the other dissolved minerals, and then a heavy sulfite treatment to scavenge the oxygen. Well, you know, it can be done with close control and monitoring. But the downside of this is reduced cycles of concentration due to all the extra chemicals being added, which is nothing more than solids. And then this leads to increased surface blowdown and then excessive loss of water, chemical, and BTUs. So again, the best overall solution is a combination of mechanical equipment to do a lot of the job and then polish the balance with a well thought out and delivered chemical treatment program, because the mechanical equipment all by itself cannot do everything. It takes chemicals to be added and monitored for this system to properly function in a reliable and efficient way. Very, very important. Now, When it comes to mechanical removal of dissolved solids, there are a couple of pieces of equipment we could also be discussing today, including reverse osmosis, or RO, and demineralizers, but the time we have just wouldn't allow for it. So what I'm going to do is I'm going to concentrate on the most commonly found mineral removal units, which would be the water softener and the dealkalizer, and we'll start with the water softener. Now, what you see here on the screen is what we call a sodium zeolite water softener, using what is referred to as cation exchange. That's C-A-T-I-O-N exchange, which removes the calcium and magnesium from the feed water before it goes into the feed system, well before the boiler. Now, the one you see depicted is a duplex unit, meaning while one of the tanks is softening, the other is going through either a regeneration cycle or is in the standby mode. Now, I referred to cation exchange. Now, what this means is we have specially designed resin beads in the softening tank, which allow a reversible transfer of ions. We've got stronger calcium and magnesium ions. Notice the double plus. They're exchanged for weaker and highly soluble sodium ions, resulting in soft water and sodium flowing through to the system. Now here you see an example of what I mean, with the positively charged calcium and magnesium ions exchanging for the weaker sodium ions, which were residing on the bead before getting overwhelmed and essentially just pushed off the bead. Then after so many gallons of water flow through the resin bed, it gets exhausted and it needs to be regenerated. And regeneration involves a number of steps, including a back flush of the resin tank itself to fluff up the resin, and then we go through a rinse, then a brine draw and flow across the resin beads, and then a slow and final rinse before we return to service. And of course, this can take, for you that have had experience with this, you know it can take several hours. During this time, you see something like this, with the calcium and the magnesium ions being literally bombarded and displaced with the sodium ions, while allowing the chloride ions to pass through, as they too are negatively charged. Remember, we're using sodium chloride pellets to regenerate the softener, and only the sodium is doing the work in this water softener. The next piece of mechanical equipment we'll be discussing today is the dealkalizer. Now, its main job is to remove the bicarbonate and carbonate alkalinity from the feed water. But it will also have some effect on the removal of sulfate and nitrate. Now, it works the same way as the water softener, but rather than being cation, it's an anion exchange, A-N-I-O-N. Now, what this means is we have specially engineered resin beads in the dealkalizing tank, which also allow a reversible transfer of ions. Then the stronger alkalinity ions, carbonates and bicarbonates, sulfate and nitrates, are exchanged for weaker chloride ions, resulting in dealkalized water and chlorides flowing through to the system. Now, since chloride replaces each of the ions that you remove, there is no net reduction in TDS. Now, here you see, and similar to the water softener, we use sodium chloride pellets or crystals, but rather than the sodium doing the work, the chloride in the salt, which is negatively charged, regenerates the dealkalizer and is displacing the alkalinity, allowing dealkalized water and chlorides to flow into the system. Again, the whole objective here with softening and dealkalizing is to significantly reduce the scale-forming minerals from accumulating within the border heat transfer surface and reduce the amount of TDS, limiting the degree of surface blowdown required. So, that's a bit about mechanical removal of dissolved minerals, which can play havoc with the border system if not removed or contained. But what about the dissolved gas that you see at the bottom? Dissolved gases, oxygen. Oxygen, when it comes in contact with ferrous metals, can really cause a lot of damage in a very short period of time. And you know, it's tricky stuff to deal with because the colder the water in the feed tank, the more O2 or oxygen it contains. And then as it heats up, the more corrosive it becomes, as you can see on the slide. Almost 2 times the corrosiveness at 122 degrees Fahrenheit than at 86 degrees. And to put things in perspective, oxygen has 10 times the corrosive effect as does carbon dioxide. So it's 10 times more corrosive than CO2. So we need to get rid of it before it does its insidious damage. And the best way to do that is through deaeration. Now, simply speaking, deaeration involves heating, agitating, and liberating the O2 or the oxygen from the system before it can attack the ferrous metal surfaces. Now remember, the hotter it is, the more corrosive it is. But it's that heating and agitation which also releases it from solution, allowing it to be purged into the atmosphere. Now, notice the bubbles adhering to the sides of the glass on the left. You know, some people, myself included in the very beginning, I thought that these were steam bubbles when you were heating a pan of water on the stove. But you know, actually, if you're below 212 degrees, it's oxygen and carbon dioxide being released from the water due to the drop in solubility as the temperature rises. So let's take a closer look at how we actually accomplish deaeration. Well, first of all, there are 3 types of deaerators. You have the column, you have the spray, and you have the tray. Well, didn't come up. Now, as the column type, which you don't see here, the column type is an excellent design, getting its name because of the column resting on top of the feedwater tank. Now, this column is filled with various rings, which can be made of stainless or ceramic, and they're impervious to the corrosive effects of the oxygen. Now, as you can see in the picture, regulated steam comes into the tank area and progresses up the column in the opposite direction of the water, agitating over the rings to increase the surface area and subsequent contact with the steam. Now, this water can be either raw makeup or maybe some cooler condensate which has reabsorbed oxygen and needs to be deaerated again. As the water passes over the rings and is effectively heated to, say, 5 pounds, which would be equivalent to about 230 degrees Fahrenheit, roughly 95 to 99% of the oxygen is released through the vent to the atmosphere as shown in the picture. Now, along with the oxygen, there will also be some free carbon dioxide releasing through the vent, and the amount is dependent on how much of it was converted to bicarbonate in the DA due to the pH. Now, the spray deaerator is very popular because it requires less headroom than the other designs. And operationally, it does the same thing as the column type as far as corrosive gas removal, but rather than using the packing rings to achieve good contact with the steam to drive off the gases, it uses a spray nozzle to essentially mist the raw water or condensate into a cone-like device where the steam enters, making excellent contact, heating the feed water to the saturation temperature, which could be 5 or 10 pounds. This then drives off the oxygen and free CO2 through the automatic gas vent before the deaerated water passes through the spring-loaded atomizing nozzle into the feed tank. The last design we'll be considering today is the tray deaerator, and its name, as you can see in the slide, is gotten because of the stacked trays housed in the dome above the integrated feed tank. Now, it is these trays which thin out the oxygenated feed water, allowing the steam to again get in close contact to raise the temperature of the water, thereby liberating the oxygen and the free carbon dioxide as it agitates through a very circuitous path between the trays. Now, The last thing that I wanted to talk to you about today regarding mechanical removal of dissolved minerals and the gases is controlling the TDS, or totally dissolved solids, in the border. Now remember, we have already removed most of the dissolved minerals of calcium and magnesium with the water softener and much of the alkalinity with the deaerator, but we still may have all or some of the dissolved minerals shown on the screen to deal with, especially the chloride and the sodium, because as we regenerated the softener and the dealkalizer, we put those ingredients back into the feed water. Now, to control these solids at the proper level, we use conductivity as our control point, and when it exceeds a specific level, which Debbie will get into, we automatically blow a certain amount of the boiler water from the surface of the boiler shell or drum. It's known as surface blowdown as opposed to bottom blowdown, which is used to rid the boiler of sludge and scale slough off. Never use bottom blowdown to control TDS levels. Now, in most cases, it's an automatic process with the conductivity sensor tied into an automatic valve which opens and closes based on a specific control band or differential. Then what we do is we maintain the desired level of conductivity to avoid things like deposition and possible carryover of water moisture into the supply line or into the steam line, the steam quality, which I referred to earlier. But the thing I wanted to leave with you today before turning the program over to Debbie is any surface blowdown operations, the process is fairly continuous. And depending upon the size of the boiler, this discharge into the sewer after separating and cooling the effluent can be quite expensive. Now, as you see in the picture, the red line coming off the top of the boiler is the surface blowdown line, controlling the TDS level in the shell or in the drum. The amount of effluent could be considerable, and if fairly continuous, may be an excellent source of heat recovery. So our choice is do we go to the left and allow the effluent to flow into a separator where it flashes and then is cooled before exiting into the sewer? Or do we go to the right through a heat exchanger, which is also piped to our feed water supply, and then take this cool feed water and heat it before it goes to the DA or the feed system? And you know, for every 10-degree pickup in temperature, we gain 1% in efficiency. Does that make sense? It indeed may. So that's about it for me with regard to controlling the quality of the feed water and boiler water from a mechanical removal perspective. And it's therefore time for me to pass the baton on to my associate, Debbie Bloom, to enter the scene and acquaint you with how the chemical side of the solution complements and further improves the outcome. Debbie?
Thank you, Steve. So I'm going to start the portion, well, I should say hi to everyone first. Please excuse me for being rude. I do plan to start the portion of my webinar by discussing the treatment of steam boilers as opposed to the hot water systems. We'll cover them at a little later time. So there's a lot of different guidelines out there. There's guidelines from the American Society of Mechanical Engineers, commonly known as ASME. The American Boiler Manufacturers Association also provides guidelines that cover the control of chemistry in operating boilers. And then there are a variety of original equipment manufacturing guidelines, and of course, guidelines that the water treatment companies like my own publish. And probably here in the United States, the more frequently used guidelines across all different industries are those of the American Society of Mechanical Engineers. I'm kind of fond of those guidelines just because I have the opportunity to work on them and edit them from time to time, so I'm in the group that actually produces those guidelines. If we go on and actually look at an example, Steve had a pared down version of this earlier, but this slide shows the suggested feed water chemistry limits from the ASME Table 2 for water tube boilers. They actually distinguish between water tube and fire tube, and right now there are currently 6 different tables. A second one on water tube boilers for high purity systems where they may have a turbine or a superheater or something that requires more stringent guidelines. And then there's also a separate table for fire tube design, for electrode boilers, coil boilers, and marine boilers. So there's quite an extensive variety of recommendations or consensus chemistry limits provided by them. A couple of things to note on this table is, first of all, if we look at the oxygen line, that's the first in the table, it's less than 0.007, and that says ppm, so 7 ppb. ASME assumes that you have a working deaerator in your system to limit oxygen corrosion. They also provide suggested limits, and I've got them actually in the red box here. They provide suggested limits for iron, copper, and hardness, and these are set fairly low due to the tendency of these particular constituents to form deposits and scale in the boiler. If we went to a higher pressure, for those of you out there that may have higher pressure boilers, they would be set even lower. As you go up in pressure and temperature, these particular components tend to become even less soluble, and that's the reason for their concentration recommendation. So another thing we notice on this table is that treatment isn't specified for oxygen scavenger nor for internal treatment, although it's assumed by ASME that you're going to be using both. And if we go down to the bottom of the table, they provide a line, they provide recommendations for oily matter and also for non-volatile total organic carbon. That's what the TOC stands for. So non-volatile, total organic carbon, that's the stuff that stays in your boiler. And quite often, those are contaminants or intentionally added treatments. And they would lead to carryover if the levels were very high. So those are things that we're also very interested in accumulating in your boiler. Now, for this particular table, there's actually a second column, as I mentioned, that goes to a higher pressure. It is 301 to 600 psi, and I didn't show that here just so that you could see these numbers clearly. If you actually have the publication, you can see all of the tables, or you'll have access to all of the tables. ASME organizes its recommendations by pressure range, and I alluded to this earlier. That's because as you go up in pressure, a lot of things have to go down in concentration to prevent scale and corrosion and carryover. So I also mentioned earlier that there was an entire table just dedicated to fire tube boilers, and the limits for the fire tube boilers end up being very similar to the limits that you're seeing here. And again, I just remind you that this particular table is for water tube, but water tube that doesn't have high purity restrictions on the steam, such as for turbines and superheaters and such. So now I'm going to go on to the next slide. This is the corresponding slide to the previous one that shows what the water chemistry in the boiler is doing at the same time. So we've got it for the same pressure range. And here we see suggested limits for silica because of its tendency to form scale at higher concentrations. And on alkalinity and conductivity, we like to control those from the standpoint that they contribute to boiler carryover and steam purity issues. Now you'll also notice here that the free OH alkalinity is actually not specified. That's what the NS stands for. And that's because at the time of the printing, nobody could agree as to what that number should actually be, because it depends fairly closely to the type of internal treatment program that you're actually running on your boiler. We're now in the process of going back to this document and revising it or editing it one more time and see if we can't actually insert a recommendation on that pre-OH alkalinity for each of the types of charts that we have in our document. So a couple more things here before I leave this slide. Some of you might not know the term specific conductance, or you might be just calling it conductivity. Those are certainly acceptable. For the ASME, we use conductivity or specific conductance in the unneutralized form, which means that we just measure a water sample with a meter. Some of you might call it TDS instead, which stands for total dissolved solids. That's another very old term and perfectly acceptable. TDS and conductivity are definitely related. If you multiply the conductivity value that I showed by a factor of roughly 0.65, you generally yield the corresponding TDS value. And the purer that you want your steam to be, if you have any restrictions whatsoever on your steam, the purer that you want your steam to be at a given pressure, the lower your TDS has to be in the boiler. And that's primarily because in boilers less than 2,000 pounds, a very high pressure, obviously, that most of what we see in the steam is directly related to carryover, mechanical carryover. And so it's directly proportional to the amount of solids that we have in the boiler water. And that's what a certain percentage of that is what we would expect in our steam space as well. So I'm going to go on here and we'll talk about some of the reasons. You know, we have our tables, and this is why we have our tables. In fact, this is why we have our chemistry recommendations. I'm going to bring one more up here, carryover. Those recommendations are to minimize or eliminate the formation of scale and deposits, boiler corrosion, and carryover in our boilers. When our boilers concentrate up to very high levels, then we end up having bad things happening, and that's what we're trying to prevent. Now, at this point in time, just because I know the terminology is a little different between what Steve is used to and I am used to, I'm going to clarify. Sometimes you might hear me talk about blowdown. And I kind of use that as a generic term, and unfortunately, I'm always thinking surface blowdown, although I might not say it. So when I say blowdown, and I agree totally with what Steve has already told you, it's the surface blowdown that I'm talking about, because I'm using blowdown as a means of controlling the concentration of my solids in my boiler water. So that's just kind of a heads up there. For any future references that I may forget to specify that. Some of you may be intermittently blowing down your boiler, and as Steve said there as well, that's to get the particulate and the sludge, and it's not to control the boiler water chemistry. So at this point in time, I'm going to talk just a little bit more about what happens if scaling does occur. Scale and deposits tend to form in those high heat transfer areas where steam is generated within the boiler, the very spot that really can't tolerate anything as a deposit. Deposits are very insulative. They have a lower ability to transfer heat than the steel itself, and as a result of that, we see the tube metal temperature rise whenever we have scaled tubes. And my next point there is that results in blisters and overheated tubes, pop tubes, mostly in water tube boilers. And we see definitely an efficiency loss in fire tube boilers. And then lastly on this slide, we can also get iron deposits. Iron deposits inhibit our ability to transfer heat just like the calcium and the magnesium, but we also have something else that it can occur with an iron deposit, and that's under deposit corrosion. Iron deposits tend to be more porous than those from calcium and magnesium, and because they're porous, they allow the boiler water to get in all the way to the metal surface, and that's where the boiling occurs, is down inside that deposit. As the steam leaves, it leaves all of the boiler water salts present at the metal surface. And so we get under deposit corrosion when we have a lot of iron deposit in our boilers. Okay, so now we're at the point where we want to start to discuss how to prevent these problems. We've talked quite a bit about scale and deposition and limits and everything. So we want to, first of all, minimize the feed water contaminants entering the boiler. Steve talked quite a bit about that. And we also can talk about the best treatment approach for individual systems and about accurately controlling blowdown rate. So I'm going to start by talking about the treatments here. There's three basic type of treatment programs commonly in use today. So the first, which I have up on the computer screen right now, is a precipitating type program. It uses phosphate, which is a very old, reliable chemistry. It's very cost effective. It is dosed based on the amount of hardness present in your system, and the point of reference there would typically be present in your feed water. It can be used when we have very high hardness in the feed water, but because it precipitates with any hardness present, boilers treated in this manner frequently require higher blowdown rates. We have to get rid of that precipitant. And they're also more likely to have phosphate scales present internally. I have a picture of that where we had quite a bit of phosphate scale in the boiler steam drum on the left-hand side. And then the beaker on the right-hand side just shows how the precipitation occurs with calcium and magnesium. So another type of treatment program is a threshold scale inhibitor. And these programs are a very good fit for fire tube boilers operating at pressures less than 300 psi. I've got low pressure boiler in my slide there, but less than 300 psi would be a very good representation of what is meant. They're able to handle moderate to severe hardness upsets, even better than the phosphate treatment program we discussed, because they function by distorting the crystal formation, so that crystal can't pack tightly. We can't have that tight, dense calcium-magnesium scale anymore. And they also don't form the amount of sludge that a full phosphate program will. So many people today are using threshold scale inhibitors as part of their program. And then the last or third type of treatment is a solubilizing type program. All polymer chelant programs are pretty typical of this category of treatment. They also are dosed based on the amount of hardness present in the feed water, but unlike the phosphate, these programs keep hardness soluble, and it conditions any sludge that does form from solids coming in, such as iron or precipitated material from elsewhere in the system. Boiler internals tend to be much cleaner using solubilizing type programs than they do for phosphate or the threshold inhibitor treatments, because there's no precipitate actually formed, and that reduces blowdown requirements in most situations. So if you remember, going back to our ASME recommendations, there were 3 things that we wanted to inhibit. One of them was scale and deposition, one of them was carryover, the third one was corrosion. So I want to just cover one slide here on corrosion before we leave that threesome. This graph shows the relative corrosion attack versus pH as measured. pH is measured at 77 degrees Fahrenheit. Fired boilers are typically made of mild steel. And that's not because they're highly resistant to corrosion. Instead, it's because they have the mechanical strength and the ability to transfer heat, and they have a relative, the materials have a relative low cost. Has nothing to do with their corrosion resistance. So usually the green, we control within the range of say 8.5 to 12.5 as I have on the screen there. And that's that green range that I have colored in. Now that would be for all sorts of boilers, and specifically for the lower pressure systems, less than 300 psi, we tend to maintain a pH a little higher than the 8.5. So comfortable control would be a pH of around 11 to 12.5, somewhere in that range, depending on the treatment program. And this just provides us with better protection and control when hardness upsets or contamination events occur in your system. So I wanted to speak a little bit to chemical oxygen scavenger and the types of products that we have there as well. That addresses the feed water system, so from the deaerator through the feed water line. If any of you have an economizer, the chemical oxygen scavenger is really important from that standpoint as well. We look at feeding the internal treatment programs that we just talked about into that feed water system someplace. But we look at feeding the oxygen scavenger actually into the deaerator or the feed water tank so that it gets the maximum amount of mixing and reaction time with oxygen. If we feed it later than that point, somewhere on the way to the boiler or into the boiler, you're really not getting the benefit of the chemical. It's meant to scavenge the small amounts of oxygen remaining after whatever deoxygenation you did, either by feed water tank or by deaerator. So sulfite is the most common scavenger used in boiler systems below 300 psi. And in fact, I'd probably hike that all the way up to 650 or 600 psi. That's a very good scavenger, fast-acting, fairly cost-effective. But there are also non-sulfite scavengers out there for those of you that have to have non-sulfite for some reason. Sulfite performance historically is monitored and controlled by sulfite residual in the boiler. A small change made in the deaerator or feed water tank can take a considerable amount of time, though, when you're waiting for it to cycle up in your boiler. So that's always been kind of one of the problems with scavenger control, especially with sulfite, is that it takes a while to see any change that you've made. And here's another key point, probably one of the most important points that I personally am going to make today. Just because you have a very healthy sulfite residual in your boiler doesn't mean that you've scavenged all the oxygen in your feed water system or in your boiler for that matter either. Oxygen and scavenger can exist very nicely side by side. It's very much a time and temperature thing. Do you have enough time? Do you have enough temperature? Do you have the right conditions for that reaction to go on? We'll talk about that. That's been a problem for a number of years. We'll talk about that and some of the automation we can do, some of the new testing techniques we can look at in a couple of slides here. So right now, before we leave the treatment realm, I want to talk about treatment for hot water boiler systems for a few slides. Hot water boilers are used in many different applications, ranging from as low as 140 degrees Fahrenheit all the way to 400 degrees Fahrenheit. And whether you have low or high temperature, the requirements to maintain these systems remain very, very similar. And corrosion is typically the biggest problem that we see in hot water boiler systems. These systems should have minimal water loss. And I suggest here 0.1 to 0.5% of the system volume on a monthly basis. That equates to roughly 1.2 to 6% system volume loss on a yearly basis. And this value is highly controversial. I ask 3-4 different people, and I get 3-4 different values here. The bottom line is the more makeup you have coming into these hot water systems, the more difficult they're going to be to treat. And so however you do it, focus on finding and fixing those leaks, because there's a huge payback in that, not only from the water standpoint, but also from the corrosion and deposition standpoint. As makeup water increases and water temperatures increase, oxygen becomes even a bigger problem from the standpoint of pitting, and it's more likely that you're going to see corrosion-related failures. So softened makeup is recommended, and again, emphasis on makeup. Softened makeup is recommended for all hot water boiler applications, and that's so that you avoid the problems of scaling in these systems. The more makeup that you have to the system, the more important it is, because the more hardness is entering into the system. So scale is a function of a number of different things here. I have them listed out. Temperature being higher the temperature, the worse is the likelihood that you're going to see scale occurring. And shorter holding times, this refers to the amount of makeup actually that you're using. So how long is that component, the contaminant, the sludge, whatever, going to stay in your system once it forms? So if you have a very short holding time, you're using a lot of makeup, your likelihood is that you're going to have a bigger chance of seeing scale end up in your system. Oh, I didn't quite finish that off, did I? pH recommendations depends on the water chemistry you're using, and also on some of the other things like chlorides and sulfites that might be there. Usually from a pH standpoint, we're in the range of 8.5 to 10.5 for these mild steel or carbon steel boiler systems. If you have other metallurgies in your system like aluminum and copper, you may have to modify that a little so that you protect them as well. And most programs nowadays use some sort of dispersant so that if sludge does form or deposits do form, you can semi-disperse them and they won't become a hard scale like we talked about for the steam boilers. So this particular slide then shows the 3 different types of programs that we have for hot water boilers. I've just made them generic. I've not included any product names. But you'll see kind of a trend go through these. We've got the nitrite azole programs, then we've got the molybdate nitrite azole programs, and then we've got the molybdate azole program. So there's kind of a common theme there. Again, these are specifically for hot water boilers, so we're focused in on mild steel, carbon steel elements, not some of the other metallurgies that you might see in closed loops. But starting from the top, nitrite azole program, we want to maintain our nitrite levels somewhere around 1,000 ppm or higher. We're talking about temperatures less than 300 degrees Fahrenheit, oxygen somewhere less than 1 to 2 ppm. If higher oxygen concentrations exist in your system, in other words, you have a fairly healthy makeup, then this program is really going to struggle to maintain good corrosion protection for the steel in the system. The azole is there to protect any copper in your system. And one other thing that you have to consider is that at very high temperatures, the nitrite can start to decompose. So you also have to consider that at low temperatures and high makeup, you have the potential for microbial to be a problem because you've got the nitrogen component there. So those are just some of the things that you might consider when you're choosing a program or choosing this particular program. So on then to the combination, number 2, combination molybdate nitrite azole. Again, less than 300 degrees Fahrenheit, fairly low oxygen. We've added the molybdate to the former product, so very, very similar in concentration. Molybdate's going to be there somewhere in the 100 ppm level, azole at the same concentration. This program is a little bit less prone to problems than the previous one due to oxygen, just because it's got the molybdate there. And molybdate actually likes oxygen. But, you know, we don't want to go to high oxygen levels because of the nitrite. We'll deplete that. So some of the problems with this particular program is that some areas actually limit the amount of molybdate discharge. So then you'd have a hard time using this program. The last one, again, with molybdate and azole. The molybdate is there at 300 ppm. If you're above a temperature of 250, you're going to have to go to slightly higher concentrations. And molybdate actually requires a little bit of oxygen present in the system. I've listed 1 ppm here as a starting point. These programs, you know, when we look at the various reasons for using these programs, there's a number of things that we have to consider. And one of them is cost. You know, environmental discharge limits, another one. Temperature, third one. All of these things kind of fold together, and whatever your specifics for your system are will determine which program is best for your particular operation. If you have the discharge limits or you have a very large system, you know, that might automatically eliminate certain types of programs that you can use. So going on, we're still on hot water, and I just want to say a little bit about sulfates and chlorides. Corrosion rates in these hot water boiler systems are very sensitive to increased chlorides and sulfates. And again, you're talking about basically a closed loop here. So if you've got considerable makeup coming in, you can get fairly high concentrations of both of these components. Both degrade nitrite and molybdate performance, and so you end up having to actually increase your dosage if you have higher chlorides and sulfates. And I've got a suggested limit here of 50 ppm. As you start to get higher than that, then you're probably going to need to increase the concentration of the active components that you're feeding. Sometimes I see sulfite or those alternative scavengers that I referenced being fed into these hot water boiler systems. And unfortunately, it takes a lot of sulfite to remove all the oxygen, or to even get close to removing most of the oxygen if you're fully oxygenated. So one thing that we want to consider is sulfite is not compatible with nitrite, so we don't want to overlay the two of them. We instead want to minimize the water loss, minimize the amount of makeup that we've got coming into the system, so that when we bring in oxygen-saturated water, it's at very low amounts on a total system basis, and we're more likely to be able to handle that amount of oxygen. And then sometimes if the makeup rates are really high, you may have to look at some method of deoxygenating that makeup. And we can talk about that on a one-to-one basis if anybody has those particular needs. Sulfite, when it reacts with oxygen, ends up forming sulfate. That's just one of those facts. And unfortunately, another fact is that sulfate at higher levels, and here I've got 300 ppm, causes a yellow metal corrosion problem. So if you've got something like copper alloy heat exchangers in your hot water boiler, in your boiler hot water loop, you're probably going to have problems. And some of the non-sulfite scavengers, we've had people say, well, I just won't use sulfite then, I'll go to some of these non-sulfite scavengers. A lot of them actually add ammonia to the system, and that also is a corrosion, corrodant of yellow metal. So then you would have copper alloy corrosion as well. So ultimately, you want to try and maintain an oxygen-free environment, so that, fix the leaks, find where the air intrusion is coming from, and focus on preventing those sources of oxygen intrusion for best results in your system. Now, I want to go on and talk just a little bit about monitoring and control. So I'm going to start talking about blowdown control. And again, just as a reminder, when I say blowdown, I am talking about continuous blowdown, or I think the term Steve used was surface blowdown. That's the form of blowdown that I'm talking about here on this particular slide and the next couple of slides as well. So this is a simple boiler diagram. It contains the feed water, if you look to the left, contains 100 ppm TDS. And my boiler is steaming away at 1 million pounds per day. That sounds like a lot of volume there. I chose that intentionally just because it was easily scalable. As we go to smaller boilers, if your boiler is running at 1,000 or 100,000, you can easily just scale that down, our results on this page, down to what you're actually seeing in your system. For a feed water flow, though, of 1 million pounds per hour, 1 million pounds per day, and a concentration of 100 ppm TDS, we can concentrate up 30 times. We can take that feed water and concentrate it 30 times and still be within the recommended guidelines that ASME provided us. 30 times that feed water TDS of 100 is 3,000. I have it there on my diagram. We can also look at this cycles calculation another way and just take 3,000 or whatever I want my boiler water concentration to be, and then divide by the TDS in the feed water, and that gives me my cycles as well. These are cycles of concentration. I call them boiler cycles in short. Knowing the cycles of concentration is important to us because that helps us understand or calculate what the percent blowdown is. The percent of the feed water that ends up being discharged by blowdown to keep the concentration of chemistry in the range that we want it inside the boiler. And in this particular instance, I have 3.33% blowdown. I got to that number just by taking 100 and dividing by my boiler cycles. If I had had 20 boiler cycles, it would have been 100 divided by 20, or 5%. So very simple calculation. When you blow down more water than what you need, you're wasting water, you're wasting energy. If you blow down less than what you need, you're causing scale and deposition. So you want to be at the right point for your particular chemistry, for your boiler design, for your operational conditions. And here, just a little bit more on determining boiler cycles. I use TDS in my example. You can also use conductivity, and remember, TDS is just another way of looking at conductivity. A lot of those meters out there that were reading out directly in TDS, it's really reading conductivity and then just applying a particular numeric factor to read out as TDS. And so if I'm reading in conductivity, I can get to TDS by dividing that number by 0.65. Excuse me, I've just got that backwards. I can use conductivity, and that is just TDS divided by 0.65. So if I multiply conductivity by 0.65, I get TDS. Probably confused you all based on that. For some waters, conductivity is an excellent tool. That's probably the most commonly used. And it's certainly, when we try and automate blowdown, that's exactly what we go to, is conductivity. But then there are those systems out there, if they use feed water that has reverse osmosis for makeup or demineralized makeup, or just a very, very high percent condensate return, we may not have much feed water conductivity. And from that standpoint, you know, when we try and determine cycles based on comparing our feed water number to our boiler number, we're going to have problems getting accurate cycles calculation. Conductivity will still be a perfectly good means of actually controlling the blowdown in those systems. It's just that cycles calculation that may not be very accurate. And so from that standpoint, there's some other things out there that we can do. We can use trace chemicals for cycles determination. Those tend to be inert, non-volatile, non-precipitating type materials. And then there's some other measurements that we can make instead of using conductivity. And specifically, again, for cycles determination, some people will look at silica. You know, I'm kind of on the fence with silica because I know it can precipitate. Some people use chlorides. That's kind of a hard test to run. And some people will actually use sodium, but that requires fairly sophisticated equipment to get an accurate number, usually more of a lab analysis. So again, just realize the limitations with cycles determination. And I'm using cycles. I'm trying to determine my cycles because cycles to me gives me two important pieces of information. It gives me holding time in the boiler, and it gives me blowdown rate. If my blowdown rate is high, I'm losing a lot of energy and water. If my holding time in the boiler is high, I have a greater chance of scaling and deposition in the boiler. So those are very important to me. Okay, so just to kind of leave this topic here with just an example, with and without blowdown control. And I see this all the time when I look at the data in various plants that I visit. With, we'll see something where the conductivity or whatever we're measuring is fairly constant with time. And without, you know, sometimes you're blowing down a lot, sometimes you're blowing down less. So certainly with is a better way to operate, and it ends up saving you a lot of water. It saves you chemicals because you've already treated that water, and it saves you energy. Just as an example here as to how much water we're talking about, the green lines that I've already got up on this chart represent a doubling of cycles. If I go from 5 cycles to 10 cycles, I save roughly 10% of my feed water. That's what my y-axis reads out as blowdown, percent of feed water going to blowdown. Now, if I double cycles at a different point in this curve, say I go from 20 to 40, another point at which I'm doubling cycles, that's only 2.5% of the feed water. So specifically when we talk about water and energy savings in boilers by cycles control, we're really looking at that low end. Those boilers that are running at low cycles, certainly less than 10. Sometimes you'll see a significant difference all the way up to 20. So if you went from 10 to 20, obviously more savings than going from 20 to 40. So the higher you are to start with, the less savings you're going to achieve by going to higher cycles yet. I hope that doesn't confuse everybody. But let's go on. Blowdown control is only half the issue. You know, you have to also perform some other chemical tests relative to the product itself to control its dosage. You may have to adjust the feed rate to maintain that dosage. And then sometimes there's additional parameters that you have to run just to make sure that you're not overcycling, or that those parameters, and that would be like silica and things of that nature, are in control. So testing can be done manually, or we can automate it. And I've got a manual version of some of our test equipment on the left and the automated version on the right there. So,
okay, Debbie, in lieu of time, Debbie has been gracious enough to supply us with a case study, which we won't have time for to actually just go through the whole thing on the screen, but we will take the case study and make it available to you on our website. We just need to go in and put some things up on it, some bullet points on it, so you'll be able to understand the case study, but we will make that available to you. Debbie, I think that was very comprehensive, and we've got a number of good questions, and I'm going to let Steve sum up what we have done thus far. But let me then give the ball back over to
Okay.
Steve.
All right. Well, thank you, Susan, very much. And just very quickly before we go into the Q&A, I just wanted to just go through just a few of the takeaways for today. Of course, proper water treatment, as I mentioned in the very beginning, is a combination of mechanical and chemical. We can't do it just with one. We've got to use both of those. It has a high, significant impact on efficiency and reliability attainment, is water treatment and mechanical removal. Water treatment, of course, is extremely important for that. Chemical treatment varies based on the water tube, a fire tube, the pressure, and the temperature. That's something to keep in mind as well, and Debbie, of course, discussed that with the ASME guidelines. Corrosion accelerates with temperature. Keep that in mind. Increasing cycles of concentration saves fuel dollars. And of course, she's talking about if you're concentrating at the low end and then double it, you've got significant feed water savings right there. As you go into the higher concentrations and then begin to double it, it's less. So that's an oh-ha moment, if you will. The heat from continuous blowdown, for TDS control can be recouped. Don't forget that. Take that feed water that's coming in to the deaerator or to the feed tank, and before it goes there, take it through a heat exchanger and grab those BTUs of the effluent coming out as a result of TDS control. And then hot water systems need to be chemically treated too, and that's what Debbie had just gone over. And the last thing I'd like to leave you with is monitoring and control is essential. So you've got a water treatment program, but if you're not monitoring it and you're not properly controlling it, you're dropping the ball. So with that, I think we can open it up to questions.
All right. Thank you, Steve, and thanks again.